October of 1975, regulatory agencies of Alaska informed the oil industry that the use of explosives for Beaufort Sea offshore seismic data collection would no longer be allowed. In order to overcome the environmental restrictions and seasonal operational constraints, GSI conceived, designed, and constructed a unique seismic system for collecting data through the ice on the Beaufort Sea. During the 1975 ice survey, GSI collected 280 miles of data by conventional means. Because of the speed and operational efficiency of the new system, GSI was able to collect 550 miles of data in conformity with the new environmental restrictions. This new system combined elements of marine and land data collection technology to solve a difficult land collection problem. Included in the system are GeoFix, a land-oriented satellite positioning system, the Thunder Wagon, an airgun energy source for generating seismic energy beneath the ice, and a land drag cable designed on the same principle as a marine streamer. Because of drifting and seasonal breakup of ice, no permanent position markers are possible. The use of GeoFix at selected points solved this problem. Here, Lewis Thompson is seen setting up his antenna in preparation for receiving the radio beams from satellites passing overhead. After computer reduction, this information will establish the location of the antenna within 1 meter. Higher post-mission accuracy is obtained with translocation techniques. For translocation, 2 satellite recording systems are utilized. One stationary system at a known location simultaneously recording the same satellite passes as a remote field unit. By combining both sets of data at a GSI processing center, first-order accuracy can be obtained between the 2 points. Approximately 2 GeoFix locations were established each day. The cleared seismic trails made traveling across the snow-covered ice much easier and faster. A conventional seismic Mayhew 1000 drill was used to drill 4 14-inch diameter holes through the ice at each shot point location. The 4 holes were spaced 7 feet apart, allowing the air guns to be placed into the water. In comparison to drilling shot holes on land or into the ocean floor, the ice drilling operation was accomplished swiftly and with minimal drill personnel. In conjunction with the Mayhew 1000, auger drills were used to check the varying ice thicknesses to ensure safety of the personnel and equipment. The precision and accurate aligning of the air wagon over the pre-drilled holes enabled the airgun mechanic of each individually operated string to easily and accurately position them for lowering into the icy 28-degree water. In preparing to take a shot, all units from the drill to the Thunder Wagon to the recording truck itself are closely coordinated in simultaneous efforts directed towards accomplishing the central goal of the entire crew: to record high-quality seismic data. An Arctic storm in February caused production setbacks and complete operation shutdown. But the veteran crew members' determination and superb team effort to work efficiently in the hostile Arctic environment prevailed, and the many years of Arctic experience of individual crew members was enough to overcome the potential hazards of the Arctic. The techniques and elements of marine data collection technology coupled with land data collection concepts proved to be an efficient and economical means of obtaining large amounts of high-quality seismic data in a short operational period. The air guns are lowered into the water from their heated storage area by pressing a single control button. 8 consecutive pops are taken at each shot point location. Continuous monitoring and quality control of equipment performance ensured that all systems were functioning properly. One of the main functions of the instrument engineer is to quality control the paper records taken at each shot point and visually monitor the oscilloscope displaying the data being recorded by the Texas Instruments DFS-4. One of the many factors contributing to the high production is the speed at which the air wagon and recorder simultaneously move up to each shot point location. The land drag cable is towed in two separate 1-mile sections. The drag cable proved to be durable and rugged, withstanding the severe cold weather and jagged ice with dependable performance and minimal maintenance. The geophones are attached to the main cable by a steel-reinforced pigtail. The design and construction of the geophone housing and pigtail is such that there were minimal operational problems. Operational performance of the drag cable was monitored by Bill Hayes. Occasionally, minor adjustments were made to the safety design towing harness to ensure that the proper tow forces were not exceeded. The recording vehicle easily tows the 1-mile section of cable, and a similar conventional cable truck tows the second half. The base camp moves on an average of 8 to 20 miles per day. The total distance moved depends on the production of the recording crew. The number 2 Thunder Wagon is ready to go into operation in the event of a major malfunction on Wagon 1. After setting up camp for the night and the recording crew has returned to camp, Party Manager Wilf Reed prepares the daily reports and field seismic data for shipment to the processing center. Ordering supplies and air support through GSI's Expediter and Dead Horse was accomplished with a single sideband radio. All the field data is shipped on a daily basis to the data processing center. The GeoFix field data is computer reduced by optimizing all acceptable satellite passes recorded at each individual location. The resulting computer output is a final 3D position for each location. The end product is a computer-generated CalCom map and a printed coordinate listing of all locations. After analyzing all the information, a final Mylar shot point map is produced by the drafting department. Comprehensive analysis and testing to determine signal and noise characteristics were conducted in the processing center. These determinations led to the optimum choice of the processing sequence used. Further tests were performed to finally calibrate the control parameters. GSI's TiMap computer was used to combine consecutive shots at one location as the first stage of signal-to-noise enhancement and data reduction. The data were then transferred to GSI's supercomputer system called the ASC, Advanced Scientific Computer, for further processing using the most modern techniques. The interactive terminal linked to the ASC provides a rapid and complete analysis of subsurface velocities for use in normal move-out corrections to align signal for CDP stack. The processing geophysicist is able to interpret velocities in a geologically consistent manner by inspection of implied interval velocities and the spatial adjacent information. The digitizing cursor and data tablet allow accurate and convenient input of interpreted velocities, while the 4 screens portray the information. After deconvolution, noise suppression parameters, velocity and static corrections have been ascertained. The seismic traces are combined in the final data reduction step, common depth point stack. Seismic cross-sections are produced with appropriate post-stack filtering as the final product of the field and processing effort. These provide the explorationist the means of analyzing the subsurface in the never-ending search for hydrocarbon fuels.